Hi, so today I'll describe this article, Hybrid Computing Uses a Neural Network with Dynamic External Memory, also known as the differentiable neural computer. And this is work done by Alex Graves, Greg Wine, and DeepMind and other people. On a high level, this is like they try to, in this paper, they try to describe an architecture that makes use of a neural network, a recurrent neural network, that has access to an external memory to which you can read and write. And so the whole paper is describing how they design this architecture. And this is very analogous for those of you that are familiar with a neural Turing machine. This idea was already introduced in that paper, the differentiable Turing machine. But here they go like a step further. So and they improve. So I would say the main idea was laid down in the neural Turing machine, but here they make a substantial improvement on the architecture. The main idea is laid in a neural Turing machine. I was still saying. So the main goal here is that, for instance, in a neural Turing machine, if you trained, for instance, on a specific memory. So let's first explain what this does. There's a controller, which is a neural network. In the neural Turing machine, that could have been a feed-forward neural network, or also a recurrent neural network. Here they only use an LSTM always, somewhat modified LSTM, and that LSTM interfaces with the input. So if you're doing sequence to sequence, as they normally do in this kind of example they're gonna go through in the paper, you have an input and you have an output, and these are like elements of a sequence. And according to the input, the LSTM is going to be able to output some write vectors and read vectors that are going to write to an external memory and read to an external memory, and those things, those vectors that are read from the external memory, they're going to be given as an input to the controller, to the neural controller, and those are going to determine, or is going to be crucial in determining the output. So the output is not just say the hidden states, or dependent on the hidden states here, the recurrency of the controller, but they're also dependent on this read vectors from the external memory. And here we can already see, so these are the vectors. These are like the ways that the controllers has to interface with the memory. We're going to go through those in a moment. But and here you have the memory, which is in fact just a matrix. So we have a number of columns and a size for each column. So these are like the location of the memory. Each column, each n is a location of the memory. And then these are some improvements that are introduced here in the differential neural computer. We have this memory usage and temporal links. These are the two main things that are introduced in the differential neural computer as opposed to the neural Turing machine. And these allow to do things like allocate the usage of the memory so that we don't overwrite things that we just wrote to. So there's a smart way to use the memory to avoid interference between different allocation in the memory. And then there's also these temporal links, and what these temporal links do at a high level is to allow a sequence to be read in the same order that was written to the memory. So if you think I wrote this data in a specific sequence, then the order in which I wrote that sequence, or the controller wrote that sequence, is lost, right? It is very hard, or is not native of the architecture in a normal neural Turing machine to reconstruct a sequence. But here there is a way with this this temporal links to make it so that the sequence gets recorded, and so we can go through the data in the same order that it was written to. So these are the two main improvements of this. And so I'll immediately go through to the part that I think is the most important of this paper. Which is in the appendix, and it's basically the details of how the algorithm works. which I think is the really important part of this paper. So first of all, the controller network, as we said, it is only like an LSTM with normal gates and output gate, forget gate, and so forth, and the hidden state. And the main thing to notice here is that you get an input X, and what his LSTM does is it outputs an output vector and an interface vector. So these are the way that so the interface vector is the way that the controller has to interface with the memory, and the output vector that determines the output of the network. Then so the Y. So a little bit more. So we can see as these are both dependent on the internal hidden states of the network, and it depends on the input of the network. So the output vector, it's summed with the read vectors. So these are vectors that we get from the memory, right? So through the interface vector, we get some read vector, or like the only way we can get an output from the memory is by reading it. So these are like they influence the Y. So the Y now is dependent from the output vector together with these read vectors. So it is also dependent on the read vectors, which are given to input as an input to a layer. Here the weights WR, and we can see. So, and one thing to notice here is that each time the read vector are always are a result of the memory being read by the interface vector in times t-1. So you always get them like by using the interface vector at times t-1, you get the read vector times t, and so you always get them like the next time steps. And then like they say here that it would not be possible to pass this information back to. So this arrangement allows the NC to condition its output decision on memory that has just been read. It would not be possible to pass this information back to the controller and thereby use them to determine the output vector without using a cycle in the computational graph. So what is the interface vector? The interface, or how is it composed? What variables are in there? There's a whole bunch of variables in there, and we're going to go through, and they are all crucial in how the memory works. Also, like all these components, they regulate different aspects of the memory, and we're going to go through them one by one. I'm going to skip this part where they describe all these different vectors. So I don't think it's very useful, but I'm going to try to describe the different operations. So this easiest operation is reading. So, by reading. So, like one important thing is to note is that there are multiple heads. Like modern self-attention or transformers that has multiple heads, they also had multiple heads in the differentiable neural computer back then in 2016. And so by doing the dot product between the matrix, so the memory matrix, and a specific reading head, you get so these are reading heads, these are reading weights. You get a reading vector or a read vector, so which is the same dimension as the size of the column so which is the same dimension as, let's have a look, as W, I guess. And whereas W, like the weight here, there's as many of those as there are columns in the matrix. So there's a weight, there's a weighted sum of all the possible columns in the matrix, depending on which one. So it's a distribution over different columns in the matrix, and we choose from. And everything in the differential neurocomputer is going to be something like that. Distribution over location in the memory, basically. So if we look back to the at the picture, like this will be like location, right? This one will be location, this one will be location, this will be location, this n different locations. And so with the sum of all these different things, it corresponds to your reading vector that you extract. And the same principle also holds for writing to the vector. So here you have a writing vector w here, ww, times step t, and the e here is a matrix that has the same size as m, and so but it's like filled with ones. So we decide when to write, and when you write, we decide we do the outer product with a vector that is a deletion vector, so it tells you which elements to delete, and this other is a distribution. So this matrix w is a distribution over deleting, basically, a distribution over where to delete. And then like this one is a distribution over what to write. So this is the writing vector. All these three things are all, as we can see, inputs. So they're part of the interface vector. Okay. So they all yeah. So we're basically subtracting this to 1. So this is what we're going to delete, and then writing this vector with a specific distribution over the all possible columns or all possible locations. So these are the two things that we have to do, basically, writing and reading. But there's different ways that we can define these different vectors. So there's different ways that we can choose a particular location or distribution over locations. So there's one which is memory addressing. So here they're discussing how they do this memory addressing. And there's content-based addressing, which is something very like self-attention, where they use a cosine similarity, and to determine with a vector, given a query key, the similarity to all the keys that are in the memories, right? So which one is most similar to the one to the query that is given, right? So here the query will be k, and m is like each column, in the, so we're looking at each column in the memory, right? So the cosine similarity is defined here, and so to discuss here, probably because it was not a new attention at that point, that even though it doesn't have to be exactly the same, the vector, but like even if it's incomplete or like partially similar, they're still gonna retrieve one particular location in the memory instead of another. This factor beta is how sharp the distribution is gonna be, and we can see that it's adjustable. It is itself a part of it. So it's not fixed. It is self and a part or an element of the interface vector. So you can change at each time step. And then so there's nothing particularly new about all this. There's nothing particularly different from the neural Turing machine. Where the difference starts is like dynamic memory allocation, where it define a vector u, which defines basically how the usage of a particular location. So we have all this location in memory. This u gives us the usage of that location in memory, and that is going to depend basically on what was the last time that we wrote to memory, or whether or not we just read to that particular location in memory. So how you use it, how high is the usage is going to depend on. So whether or not we just read from that specific location in memory, and whether or not we just wrote to that specific location in memory. And one was the usage in the time step before. So these are the things that so you can see here. Ut is gonna be a function of ut minus one. So what was the usage just before? Whether or not in t minus one we just wrote to that particular thing, and so this then we have to subtract this term to guarantee that this is gonna be sum up to one, because like the usage always has to be between 0 and 1. It cannot be anything like it cannot be outside this range. And this is interesting because this represents by how much each location will not be free by the free gates. So this is something interesting here happens, which is there are these free gates. For each head there is like a free gate, because there are n heads that read, and that if we just read in t minus 1 from that particular location, that f is gonna, so normally we would want to override, we would say that we don't want to use that, so we can free that slot in our memory because we just read from it, and normally we don't need that information anymore if we just read from it. But we can also choose to maintain the information there. In that case, f is going to be, if it can be freed, is going to be like 1, right? So then, like all this element for each of the heads, we go through each of the heads, and if for instance for each of the heads this was 1, that meant that whether or not can be freed, and then like then this element here is going to be 0, which will mean each location will not be freed. If it's 0, it will be free, basically. So f just determines whether or not we can free something that has just been read, and then like all these other elements are just obvious, right? We maintain the usage at t minus 1, plus if we write something that is going to increase the usage, and if we just write something that is going to decrease like the usage or not, depending on this f right here. Okay, then the usage is going to allow us to, we're going to rank this usage using phi, and basically phi of j is going to basically, if we have phi of 1, that's going to be the least used location. So it's going to be the index in U that gives us the least used location in the memory, right? So we rank them basically, and a, now we calculate a, which is itself a value between 0 and 1, which is going to tell us how whether or not to allocate how much. Is going to be a distribution of allocation over different different allocation in the memory, right? Different location in the memory, and this is going to be dependent on how much. So for j is going to for the j is going to just be, so what comes out of this is just the, so if we have like this one, if it was j was 1, we would have the index of the least used like element of u, and if it was 2, the second least used element of 2, and so forth, right? So we go through these following the order, so the ranking of the least used, and how much we allocate to them is going to depend on how much is free, so 1 minus the used space, and it's going to depend if it was very free or not before. So think in terms of like in binary, if this was like all 1s, that meant like all the 1 before have been used pretty a lot, right? So you would like use this 1 a lot if there was or this index, this location, you use it a lot because you haven't used the 1 before. The 1 before, there should be more free than this one. So to the extent that you haven't used, to the extent that the other one before are free, you're not going to use this one, this particular j. And to the extent that the one before were not that free, you're going to use this one. So the less free are all, because you're going to start from the least used one and like scale down. To the extent that you've used already those, you're going to use this one less, right? So it's a combination of these two factors. How much usage you have, and how much have you used the one that are freer than this one in particular. I know it sounds a little bit confusing. I'm going to put a link in the description of a blog or a description of this differentiable neural computer, which is really, really clear and does a much better job than I could ever do in explaining this. But yeah, bear with me. So another way to like write vectors to memory or write to memory is with a content-based addressing. So this will be the same thing that we already discussed, the attention-based mechanism with a cosine similarity, only for reading, for writing, sort of for reading. And when we we write, we can use a combination of these two things. So A is going to be this allocation based on the memory usage, and C is going to be the one based on content. And we're going to have a gate that's going to decide how to weight this. It's going to be a distribution between these two methods, and like this thing, which is going to be an interpolation JW. So JW is the write gate, whether or not to write to a specific location. And so now we jump to the temporal link matrix, so which is the next. So we covered usage now, which was one of the new features of this differentiable neural computer. And now we jump to L, which is this temporal linkage or temporal link matrix, which is the other innovation of differentiable neural computer. So it has to allow us to go through the sequence in the same order that we wrote it to the new differentiable neural computer. So Lij represents the degree to which location I was the location written to after location j. Okay, so this is basically the definition of what L is. It gives us the degrees to which location I was written before location j. And if you think about 0 and 1, and in terms of 0 and 1s, there's going to be 1 if location I was written to after location j, and 0 otherwise, right? And so perfect. So in that way, if you think just in the matrix was just 0 and 1s, you will be able to retrieve, I don't know, if I give you a vector of 0, 0, 0, and then 1, for meaning intended to mean location 3, and then like multiply by this set matrix L, that will give us what element would came before element element 3, right? So it will tell you, I don't know, element 1 came before element 3. That is useful to do this retrieval of the sequence in the same order. So how do you define L, right? Because that's a tricky part. To define L, we need another quantity, which is another vector, which is this vector P. And P represents the degree to which location I was the last one written to. So, and is defined by this recurrence relation. It starts to 0, so for every element, we can make this distinction to which one was the last one being written to, or like what was the extent by which any of these elements were the last one being written to. But at each time step, we take basically this P at a time step before, and since it means the degree by which it was the last location being written to, anything that has been written in this time step for T, so everything that was written, we take all this vector as that write, and we sum them up, and by the extent in which anything has been written at this particular time step, we have to decrease the strength of any element in P t minus 1, because to the extent we write this in this time step, we have to decrease the extent by which elements in the previous time step were the last one being written to. And then we add how much are we written to, so the elements that we've written to this time step, So we add to each one of those elements the strength by which we're writing in this time step. This is also a little bit, I find it a little bit confusing, and it's pretty convoluted, but it's but it works. It makes sense. And I refer to the previous blog for any more details. And then to define basically the linkage or the link matrix, we say, okay, the previous element at this particular location here, ij, lt minus 1 ij, so the previous, the element in the same location in the previous time step, we should weaken its relation by the extent to which we are writing to both those elements in this particular time step. So if this is supposed to measure how much I was written to before j, or the opposite, if we write to I and j at the same time, this is going to weaken this relationship. And then we wanna increase it or strengthen this relationship by the extent that we write to I and we wrote to j in the previous time step. So exactly, just by following the definition of what Lij means. Okay, and this allows us to define like this b and f, which are themselves also something that comes with b and here. I mean, I cannot see b, but this should also be things that come here with interface. Oh no! These come from here. Sorry. So, by multiplying this L or transpose of L by a certain weight, by a certain vector, sorry, we can get what was the distribution of location that were written before the distribution of location that we defined by W. So W is going to be a distribution over location, and by doing the dot product with L, is going to give us a distribution of location that were written before or after. So here before and here after. So this forward is backward, and this way we can either go forward in a sequence or go backward in a sequence. If you think about this in terms of in binary terms, it makes more sense. But then it's defined in terms of distribution. So you always F and W and L are all like distribution over locations, which is done to make the whole thing differentiable. And so here to talk about a little bit of what they did, because this L is it's too big. There's a link matrix. It's n by n, and as this becomes bigger, they need too many operations to perform all the machinery that we just discussed. So they just they try to make it more sparse, in that way saving some computation time, and they do that by just taking putting having a sparse matrix where only the k element, the k first element of each of these vector p and w are non-zero, and all the other are non-zero, and they try to make it so that they all sum up to 1, obviously, but there's some tricks that they use there to decrease the computational load. So then here, when you read, you either can do this by like the backward relation. So this is pi. It gives a distribution over different methods that you can have to read from memory. You can have the context-based or content-based method, the same one that we discussed before, using attention or the cosine similarity. You can have this going forward in the sequence, or backward here. And this is how you read for each of the heads. And so here to talk a little bit more about the differences between NTM a neural Turing machine and this, their base will come down to this link matrix not being there and the usage, and yeah. So I want to go over maybe a little bit the different experiments that it did, maybe very quickly. So one of the experiments they do is like on this random graph, they take random steps in the graph, and so first they give the whole graph to the network. So they just define all the nodes in the graph to the network. And this is done, for instance, one of such graphs is the London Underground map. And for each pair of station, they give the edge. So the edge will be the line here, which line you could use, or the line number, or you can use, or the line name that you could use to go from one station to the other. And this should be adjacent vertices. And so forth. Like they define all these different nodes. And then what they do is like they take a random, they start from a specific location and they take a random edge, and they like take that edge and they go to that edge. Like they go to the next vertex by choosing that edge. And they do this for a number of times, basically effectively doing a random, assuming that these vertices, or no, these edges have like a direction, they're like oriented. You're like doing a walk on the graph, a random walk on the graph, and then like what the network is supposed to give you back is the list of all the nodes that you, or vertices that you visited, because you're not given those, right? So he has to compute which node you went to, and basically retrieving from those that you were given before. Another one is like given two stations, has to give the network has to return the shortest path between those two things. They have some other example with a family tree, or yeah. So here we can see that in this graph examples, the DNC reaches an average of 98% accuracy, whereas other things, other architecture like the LSTM, here they only talk about the LSTM. They say that they did an extensive hyperparameter search, but they don't say if they did a hyperparameter search for the DNC, which is weird. But they did say that for both they did a curriculum learning. Otherwise, even with this very good architecture, the DNC, they still wouldn't be able to perform well on these tasks. And well, it's a pretty big jump in performance on these tasks. And then they have another experiment where they give, so these experiments look like this. It's like this grid of blocks, and they give a goal, so a goal state where they have what we want a position between two blocks to be true or to be realized in the configuration of blocks here. So for instance here 6 below 2, or 4 left 1, so 4 has to be to the left of 1, and so forth. And the network has to move these blocks around in order to make this realized. So this is the input, and the initial configuration I will take is also an input, and then the network has to move things around. And I believe this task is a reinforcement learning task that is maybe, I think, I'm not sure though, that the reward is only given at the end of so only when this state is reached, and not otherwise. So it's not supervised learning. Yeah. And also here, let me see if they report any increase in performance. So about the performance, they say, so they have this curriculum learning also here, where they gradually increase the number of blocks on the board and the constraints, so in the goal, and the number of goals, and the minimum actions of, so probably this things go together, minimum numbers of action you need to find a solution, and they show here, so this critical learning as you move, so as the lessons become more and more difficult in this critical learning, the LSTM gets stuck to some of these. Gets stuck to around 10 in these lessons, and whereas the DNC basically does as no, they make us think that the DNC, I guess, would be able to perform still pretty well on problems that are much larger. But yeah, these problems are all like, and this is done with reinforcement learning. So this block problem, this block puzzle. These are all like, it's pretty exciting what it can do. I mean, of course, this paper is like fairly old, and a lot of stuff has been done. I mean, of course, now we have transformer, but this is still different. I feel like it's not really useful for natural language processing and that kind of applications. So it has not been worked on as much as other kind of architecture. Of course, now we have transformers, but they're something different. They share some property with this differentiable neurocomputer, but I still think that they're different. And so there was the differentiable neurocomputer.